Now that we know what a polar bond is, we can look at polar molecules. So the molecules all together, they can be polar or nonpolar. And recall the five shapes that you needed to know. You need to know the shape linear, you need to know the shape trigonoplanar, the shape tetrahedral, and then we have pyramidal and bent. So those are the five shapes that you need to know. So let's look at molecules being polar or nonpolar altogether. Rules number 1 and 2 have to do with it being nonpolar, and rules number 3 and 4 are more concerned with polar molecules. So let's look at the first rule. So if the molecule has no polar bonds, it's nonpolar. There's nothing there that will give the molecule a positive side or a negative side. So for example, if we look at methane, methane has 4 carbon-hydrogen bonds, and recall that the carbon-hydrogen bond is nonpolar. So if I take all these nonpolar bonds and stick them together, they're going to be nonpolar. So there's nothing there that will give it a negative or a positive charge. All right, rule number 2, if the molecule is symmetrical, and in chemistry what that means is it has all the same bond. And it's not mirror symmetry, it is radial symmetry. So around that central atom, all the bonds should be the same. If everything is the same, then if I have polar bonds, they will cancel out. So for example, this is carbon tetrachloride. When you look at each bond there in that carbon tetrachloride, you see that I have polar bonds. There's 4 polar bonds. The chlorine is more electronegative than the carbon, and so you will have those arrows pointing out. So, but I have the same polar bond all the way around. And because of that, this molecule is symmetrical. So the polar bond, it is a vector, so it has both magnitude and direction. And when I have them coming out of the central atom at all the same angle, all the way around, evenly distributed, it has symmetry, and they will cancel, those polar bonds will cancel out, and I will have a nonpolar molecule. All right, let's look at the rules for if it's polar. So if your molecule has at least one polar bond, the molecule is going to be polar, and it will not be symmetrical. So looking at this first example, which we had in the last slide, we have the carbon tetrachloride. It's the same bond all the way around. It will be nonpolar because all the polar bonds will cancel. Look at this next example. We have everything the same until we get to the hydrogen. And because the hydrogen carbon bond is different than the carbon chlorine bond, this is not symmetrical and it will be polar. Again, it's polar because it's different. We have a different bond all the way around. So you can just look at that central atom. If there's anything different, you automatically know that it's going to be polar. There are 2 shapes that just knowing what this shape is, it will automatically be polar. And that is trigonal pyramidal or bent shape. And that's because it has these unbonded electron pairs. Those unbonded electron pairs, that is where it's going to be a little bit negative. Over here by the hydrogens, they will be a little bit positive. And this next one, we have water. Right by the oxygen, it will be a little bit negative. Right by the hydrogens, it'll be a little bit positive. So these are polar molecules. We can draw the little arrows that show their polarity by drawing it through the molecule, pointing up where it is negative, and down at the bottom you'll have a little plus sign. So again, if the molecule are these 2 shapes, trigonal pyramidal or bent, it will be polar, and it's because of those unbonded electron pairs. So in that lab that you should have started, you should go through in the last 2 columns, identify if it's symmetrical, and then if it's polar. Remember, it is symmetrical if it has the same bond all the way around. Everything has to be same. And then if everything is the same, it will be nonpolar. If you have any bond that's different, you automatically know it's non-symmetrical and it will be polar. Let's look at a few more examples. We have water right here. We've looked at that before. It is a polar molecule, so you can see the polarity. It will be a little bit negative here at the top, and it will be a little bit positive down here. And this next one, let's look at the symmetry. We see that we have 3 carbon-hydrogen bonds and 1 carbon-fluorine bond, and it's different. So if it's different, then you know that it's going to be polar. Fluorine is the most electronegative, so it's going to be negative up there. Our carbon-hydrogen bond is a nonpolar bond, and so it is not going to be able to pull on the electrons in the bond as much, and so you're going to end up with this polar molecule with the arrow going straight through the molecule. Okay, let's look at this last example. So in this last example, the carbon-oxygen bond is a polar bond. You can see oxygen is more electronegative than the carbon, but look, you have the same bond all the way around. There's only 2. And because it's the same bond, this will be nonpolar. It is symmetrical. We can look at different models. We have our Lewis structure over here on the left. The ball and stick model, you've seen that in the class. These last 2 are a little bit different. So the third one is called the space filling model. And then the last one shows an electron density. And so you can see this is a nonpolar molecule because it's the same bond all the way around. Also, that carbon-hydrogen bond is nonpolar. So you can see when you look at that methane molecule that there's no shifting of electron density, that everything looks just about the same. All of these molecules here are polar, and that is because they are not symmetrical. So looking at the first one, we have different bonds, and so we know that it's polar. And so in this part of the molecule, it's a little bit negative, and this one's it's a little bit positive. In this next one, we have 2 fluorines. So between the fluorines, that is where your polarity is going to lie. And so there's going to be a shift in electron density. And then we have water over here. So water we've looked at, this is the 3rd time. It's just a good example of polarity. And look at this next one. So if you're confused about the symmetry, you might say, oh, it's symmetrical because it's a mirror image. But remember, it's not mirror symmetry or bilateral symmetry that we're looking at. It's radial symmetry. It means that everything has to be the same. Over here, this is a nonpolar group, and that's a nonpolar group. But in the middle, this is polar, and so that will make the whole molecule polar. So you will have your polarity like this.